Mohr's circle is a graphical representation method to find the principal stresses of a stress element subjected to a specific stress state and the angle at which they are found. A 2D stress element at any location inside a structure is characterized by the stress components sigma x, sigma y, and tau xy. These are typically caused by some or all the stress types we have studied in the previous videos up to this point. For example, for a simple cantilever rod subjected to a point load and torque, we can study the plane stress element on two different locations, A and B. We would see that stress element B is subjected to a positive normal stress in the x direction due to the bending moment caused by the point load P. The moment would be equal to P times x, the distance from the stress element B to the point load P. The value for y would be the distance from the neutral axis to the top of the beam, which is the radius of the rod. Since stress element A is located on the neutral axis, the value of y would be 0, and therefore stress element A would not be subjected to this bending stress. Stress element A is instead subjected to a transverse shear caused by the shear force P. B would be equal to P. Q can be obtained by multiplying the shaded area of the semicircle above A times the distance from the neutral axis to the centroid of that semicircle, and T is the thickness of the rod at the point where we're trying to calculate the shearing stress, which is the center of the rod, and therefore T is equal to the diameter of the rod. The second moment of area I would be that of the whole circle, not just the semicircle, and it applies both to the shearing stress of A and the normal bending stress of B. If we look at this shearing stress equation for stress element B, we would see that the value of Q is 0, and therefore B is not subjected to this shearing stress. However, due to the external torque T, both stress elements A and B are subjected to a torsional shearing stress. The total stress of element A is of course just the sum of the two shearing stresses. For stress element B, however, we have both a normal stress and a shearing stress. And of course, we wouldn't compare them individually to a maximum allowable normal stress and a maximum allowable shearing stress respectively. What we know about a material in the real world is its material properties, such as the yield strength or the ultimate strength. For this reason, it's important to find the maximum values of the shearing stress and the normal stress at location B for when the stress element is rotated, and the angle of rotation for which that stress element yields the maximum values of stress. For example, if we look at a rotated stress element at location B by a certain angle theta, the resulting normal stress, which can be calculated by adding all the components of tau xy and sigma x in the direction perpendicular to that phase, is higher than the original normal stress sigma x. And for another value of theta, even though the resulting normal stress sigma x prime is lower than the original sigma x, tau x prime y prime, the resulting shearing stress for that second angle of rotation, would be larger than the original tau xy. The two angles theta, for which we find the maximum value of sigma x prime and the maximum value for tau x prime y prime, are important for some applications, but we mostly care about the maximum shearing and normal stresses. For any given rotation theta, we can find an expression that allows us to calculate the new normal stress sigma x prime and another one for tau x prime y prime. Optimizing the values for these expressions, which means finding their maximum values, can be done either mathematically by taking their derivative and solving for 0, or graphically by plotting their functions and finding the maximum values. This graphical alternative is what we call the Mohr's circle. If we have a stress element subjected to sigma x, sigma y, and tau xy, and we want to find expressions for their resulting sigma x prime and tau x prime y prime for a rotated stress element by an angle theta, we can just perform a cut at that angle theta and write the sum of forces for the new x prime and y prime directions. Since we need the areas to transform stresses into forces, we will assume that the hypotenuse has an area delta A, knowing of course that this plane element is actually 3D and it has a certain depth in the z direction. For the sum of forces in the x prime direction, we have sigma x prime times delta A in the positive direction and the components of the other four vectors in the negative direction. For example, for sigma x, we would have its component on the x prime axis, which is sigma x cosine of theta, affecting the left face, which is the component of the hypotenuse delta A cosine of theta. For the sum of forces in the y prime direction, we have tau x prime y prime affecting the hypotenuse, the y prime component of sigma x, which is positive and affects the left side of the triangle, the y component of sigma y, which is negative and affects the bottom side of the triangle, the component of tau xy on the left side, and the component of tau xy on the bottom side. Since the stress element is only deforming and not moving up or down, we know that the sum of forces are equal to 0. And since every term has a delta A's cancel out, and we can write simplified versions of each equation. Using the trig identities for the double angle for 3 of the terms in these expressions, and the trig identities for the cosine squared and the sine squared on the 2 first terms of the first equation, we can group some of the terms together for the expressions of both sigma x prime and tau x prime y prime. Now, if you remember from simple algebra, the equation of a circle is x squared plus y squared equals r squared. The parametric equations of a circle, which are those that depend on a parameter, in this case the angle theta, would be x equal to r cosine of theta and y equal to r sine of theta. You can try it out with any value for theta, but for example, for theta equal to 0, x would be equal to r and y would be equal to 0. To go from these parametric equations to the equation of a circle we know in Cartesian coordinates, we square both sides and add them together. This can always be done as long as the axes, in this case x and y, are perpendicular between each other. This is true for the 2 expressions derived, since sigma x prime is perpendicular to tau x prime y prime. And notice that the parameter in this case is 2 theta, not just theta. To go from parametric to Cartesian, we square these expressions and add them together. Since the first term on the right-hand side of the first equation is not dependent on the parameter 2 theta, we can move that to the left-hand side of the equation. The right-hand side would be 2 terms added together and squared, which is equal to the first term squared plus the second term squared plus 2 times the first times the second term. We do the same for the second equation, knowing that one of the terms is negative, and therefore the 2ab term is also negative, and we add the 2 equations together. The left-hand side is just adding the 2 terms together, and on the right-hand side we see the same term, factor of sine squared plus cosine squared, which is a 1, a second term, factor of the same trig identity, and a third term that cancels out. One last concept to remember from algebra is how plots of functions can be shifted left and right by adding or subtracting from x. For example, x minus a instead of just x in the equation of a circle would be a circle that is shifted a to the right. And this is exactly what we have in our resulting expression. Sigma x prime is the x variable, tau x prime y prime is the y variable, the shift a is the location of the center of the circle, and the radius the square root of the right-hand side. Remember that the parameter that we used for these expressions was 2 theta, not just theta. So whatever angles we use in our plots will be 2 times the angle of rotation in the real world. Let's take a look at a simple example where we have already found the stress state for a specific location within a structure. The center of the circle for this stress element would be located at the average of sigma x and sigma y based on the expression we just derived. From the other expression we derived, we know that the radius of this Mohr's circle is 50 megapascals, which tells us that the circle reaches a value of 20 plus 50 on the right and 20 minus 50 on the left. The y-axis, which is the axis for the shearing stress, would be located at x equal to 0. The convention that most textbooks use for this axis is that we plot clockwise shearing stresses on the positive axis and counterclockwise shearing stresses on the negative axis. The original stress state can be located on the Mohr's circle as capital X and capital Y. If we use the given values for sigma x and the vectors of tau that affect the same side, we'd see that the location of capital X is located at minus 10 for sigma, and a vector of 40 megapascals that is trying to make the stress element rotate counterclockwise. The location of capital Y would be positive 50 for sigma, which affects the top and the bottom face of the stress element, and the tau value of 40 coming from a vector that is trying to rotate this stress element clockwise. With simple geometry, we can calculate the angle between the diagonal capital X capital Y and the sigma axis. This is the angle for which capital Y becomes the maximum stress, or what we call a principal stress. We call this angle theta p for principal. Tangent of 2 theta p would be equal to 40 over 30, or in general, the vertical side of the triangle, which is tau xy, over the horizontal side of the triangle, which is the sigma distance between capital Y and capital X divided by 2. This expression would give us the angle from the horizontal line to the diagonal. So if we want the angle from the diagonal to the horizontal line, we need to add a negative sign, which is the same as changing the order of the subtraction. Besides obtaining this principal stress angle, what we did here was use the given stresses to find their maximum normal stress and the maximum shearing stress, which we call the principal stress and the maximum in-plane shearing stress. We know that if we were to look at a stress element that has been rotated 26.6 degrees clockwise, the given stresses sigma x, sigma y, and tau xy would contribute with their components to yield a maximum normal stress possible. 70 for the face that was once the y face, and minus 30 for the face that was once the x face. The same process can be carried out to find the maximum shearing stress. The angle of rotation to find the maximum shearing stress could be found by using the reciprocal of our previous expression. A stress element that has been rotated 18.4 degrees in the counterclockwise direction would show a positive stress of 20 megapascals in both the x and y faces, and the maximum shearing stress possible. If we follow the y phase, we would find a vector of 50 that is trying to make the stress element rotate clockwise. And if we follow what used to be the x phase, we would find a vector of 50 that is trying to rotate the stress element counterclockwise. It is very important to understand where the stress element with the maximum shearing and principal stresses is located within the structure. For example, the stresses for A are going to be the same along the x-axis, whether we're close to the fixed wall or close to the free end. However, for stress elements on the top of the rod, like B, the moment is a function of x. So, as we move farther away from the force P, the value for the moment increases, and therefore the value for the normal stress increases. So we know that the stress element with the maximum stresses would be located near the wall. For more complex structures, you usually have to consider more than one location, and you need to find the principal stresses for all of them to identify where the structure would fail. If you want to see how some of these problems are solved, as well as other more circle examples and the other 10-minute lecture videos of the Mechanics of Materials course, make sure to check out the links in the description below. Thanks for watching.